Hello everyone, my name is Tabish, and today I'm going to be showing you guys a trick that can be used to visualize population models, or really any differential equation that involves equilibrium or um, a solution where it's like the left-hand side is only the dependent variable's derivative and the right-hand side is only a function of the dependent variable, like dp over dt equals some function of p. So to start, let's just start with some population model. So we can have some model like dp over dt, and let's just say like 6p minus p squared. So what I'm about to show you guys is something that one of Professor Manford's videos briefly touched on in Unit 3, and something you had to do on your homework, but today we're just going to take that and take it one step further. So to try to visualize what this solution would look like, the first thing we want to do is, of course, to find the equilibrium points. And how do we do that? Well, what you guys are thinking is probably right, because you're probably thinking that we could just factor it out. And that's exactly right, because that would show us that our two equilibrium points would be p equals 0 and p equals 6. And with that, we know that those are the two levels that our equilibriums will be at. So they'd be like at y equals 0 and y equals 6. But now we want to find out the behavior of like anything that's between these, or any like value in here. And to do that, something that I know a lot of people have been doing is like taking values that are below 0 or greater than 6 or between 0 and 6 and plugging them back into this equation. And that does work and it gets the job done, but there's an even quicker way to do it. So what if we just take this guy here, our population model, and plot him as his own function of p? And we can use y or any variable, but if we plot him as p, we get this parabola. And sure enough, the zeros of this parabola are the same critical points that we just saw. And with this is exactly what we expected, because what we just did is find the zeros of this quadratic equation here. But there's also something more that this parabola can tell us. If we look at the values of this parabola before, between, and after the two equilibrium points, we see that before 0, it's negative, between 0 and 6, it's positive, and after 6, it's negative again. So if we take that information, we know that that tells us that if we graph our solutions, the way our solutions would behave, below 0, our solutions would want to go negative. And then between 0 and 6, they'd want to go positive from 0 to 6. And then after 6, they'd want to go negative and come back to 6. And we know that just from whether these values are positive or negative at certain intervals. And with that, we can see that anytime that you like graph this here for any function, if it ever goes from negative to positive, that's going to give you an unstable solution, because things will want to go away from the equilibrium above or below it. And if it goes from positive to negative, that will give us a stable solution, because things are going to go up to the solution or come down to the solution. But something super cool is anytime that you graph a function and it crosses or touches the x-axis at all, that'll give you an equilibrium. And the reason I said touches is something that we're going to get into right now. So let's try out a different function. How about we go like p squared times p squared minus 9. And let's graph this guy and see what he looks like. So this gives us this function, which is like a quartic function, because we know if we factor these out, we have like p to the fourth and p squared. But let me just change the zoom and make it easier for you guys to see. Okay. So with this, we see that the same rule that we had applied before, and we see that it's given us three zeros, or three equilibrium points. We have -3, 0, and 3. So I'll just graph those for you. Okay. And we can see that the same principle applies, because here we see that it's going to be positive and go negative for -3. So for -3, it's going to be a stable solution, because things are going to want to go to -3. For +3, it goes from negative to positive, so that's going to be our unstable solution. But we also have one more equilibrium value here, and it's at 0. And we can see that even though the function reaches 0 here and it touches the x-axis, it doesn't cross. But if we look at this further, we can see that before and after 0, the function is negative, which means that here, whether we're above or below 0, the function is going to be going negative. So what that tells us is that 0 is an equilibrium, but it's a semi-stable equilibrium, since it It's neither stable nor unstable. So if you ever graph a function and it touches the x-axis but does not cross it, it's going to be a semi-stable equilibrium. And I just have two more examples. This one's pretty quick. So if we have like e to the p minus 1, this is just to show that we can graph functions that aren't like parabolas or cubic or quartic functions. They still do the same thing. So if we have this guy, we see that he crosses the x-axis at 0, and that's their equilibrium point, because if you plug in 0, you get 1 minus 1, which is still 0. And this, even though that's their only solution or our only equilibrium, it's still going to be an unstable equilibrium because we go from negative below it or before it to positive above it or after it. And then this is the last example, and this one is actually pretty cool. Let's get rid of this. So this one, I'm going to actually go back to our original population model that we had. And what I'm about to show you now is something that Professor Manfroy touched on in one of his videos. And that is actually if we're like hunting or harvesting members of the population. So say this is a group of fish, and we're going to go fishing, and we're going to take out X amount of fish from this population. So we can see right now it's just showing the population unaffected, thriving on its own. Say we like go and we decide to fish like one fish. We see that now the equilibrium values are getting closer together. And this is exactly what we'd expect to happen, because as we increase this, those values are going to keep getting closer together. This window of space, or of values rather, where the population can dip and still go back up to a stable equilibrium, or aka the second equilibrium point, is getting smaller and smaller. And this is also what Professor Manfroy was showing you with the thing that looked like a sideways parabola that was sort of displaying the equilibrium values getting closer together as this hunting or harvesting value increased. But the cool thing here is, say we keep hunting these guys. We can keep going and going. Now we're at 1 and 5. We can keep going even further. So we go to 8, we're at 2 and 4. So we have a really small window. Let's go even higher. 2.5 and 3.5. But what if we go to 9? So if we go all the way to 9, we see that what we've done now is that there's only one equilibrium point. There's only one, and that's at y equals 3. What we've done now is that equilibrium is semi-stable, and it's negative both above and below. So while this equilibrium does exist, we've hunted the population to the point where that equilibrium is very delicate, because it's gradually like dipping to it, and if it dips below that equilibrium, the population is going to decay to extinction. But now, say even after this we keep hunting. If we add even a little bit or hunt even a little bit more, that population is going to no longer touch the x-axis. And what that means is that there's no longer an equilibrium. The population is now always going negative. It's always decaying, no matter where it is. So this is going to look something kind of like this. This is kind of like the shape that it would take. And we see that we can kind of see where the equilibrium used to be, but it's not there anymore. And this is plus 3 just because like it's going to still be at 3, wherever the final quote-unquote equilibrium was. So I hope this video was helpful, and let me know what you guys thought. I hope your midterm studying is going well, and best of luck tomorrow. Thanks for watching.